I'm gonna have a look at an exercise on the Fourier transform. Let's say what is f times f hat times f hat bar. What is that quantity? F hat is the Fourier transform of the function f of t. And f hat bar is this integral, and you take the conjugate complex, that's a complex number. So f hat, we can rewrite this in the following way. We will use Euler identity for the exponential because it's a complex exponential. So that is cos omega t minus I sine omega t dt. Let's split this integral into two parts. So my f hat is a complex number of this form. And I take the conjugate complex number. It's going to be this one conjugate, so it means that it has the same real part and opposite imaginary part. Now let's take the product between the two, f hat times f hat conjugate. So it is this this quantity here times that quantity here at the bottom. So that is going to be what? The integral from 0 to infinity f of t cos omega t dt squared plus the integral from 0 to infinity f of t sine omega t dt squared. So let me write underneath f hat times f hat bar equals the integral from 0 to infinity f of t cos omega t dt squared plus the integral from 0 to infinity f of t sine omega t dt squared. That's the final answer. That's what I was looking for. Now if you, let's say that you take f hat over f hat bar. The numerator is the integral from 0 to infinity f of t cos omega t dt minus the integral from 0 to infinity f of t sine omega t dt. And the denominator is the same thing, but with there's an I here. These are two conjugate complex numbers. So I have to multiply the denominator by the conjugate complex number, So that's integral 0 to infinity. The numerator stays the same. I rewrite it. And I multiply by the conjugate part of the denominator, which is basically, it's going to be that one with a minus, is going to be squared here. And the denominator is the integral from 0 to infinity, f of t cos omega t dt squared, plus the integral from 0 to infinity, f of t sine omega t dt squared, I use the identity to expand the numerator. Minus 2 integral 0 infinity ft cos omega t dt ft sine omega t dt, plus this part squared, so it's going to be I squared, it's going to be with a minus the integral from 0 to infinity f of t sine omega t dt squared over the integral from 0 to infinity f of t cos omega t dt squared, plus the integral from 0 to infinity f of t sine omega t dt squared. Now the real part of that, I separate my complex number. It's going to be 0 infinity I just polish the formula a little bit. And now I have to find I need to write the imaginary part, minus 2i integral from 0 to infinity f of t cos omega t dt integral 0 infinity f of t sine omega t dt, and the denominator stays the same. Yeah, I think that's a good exercise. I have used the Euler's identity for the kernel function, since it's a complex exponential, to find an explicit expression of f hat, which is the Fourier transform of the function, times the Fourier transform of the function conjugate. So basically what I get is this formula with a square. So you have these two integrals which are contribute from the complex exponential, and then you take f hat over f hat conjugate, and basically the denominator is you take the integrals square and you add them together. Here I have the difference of the two integrals, and this term minus 2i integral the product of the two integrals, and the denominator is the same here. It's a pretty cool exercise, I think, because Euler's formula managed to combine the complex exponential and managed to appear at the right hand side, the cos and sine, the two very significant wave functions, the two trigonometric functions.